Welcome back to the video lecture series on strength of materials. Today we will discuss the topic shear force and bending moment diagrams. Myself Dr. P. Pramod Kumar, Associate Professor of Mechanical Engineering, MLR Institute of Technology, Hyderabad. In this lecture, we are going to study shear force and bending moment diagrams for cantilever beams. First, we will see how to draw shear force and bending moment diagram for a cantilever beam carrying point load at its free end. Next, we will see shear force and bending moment diagram for a cantilever beam carrying uniformly distributed load over entire length. Let us start the shear force and bending moment diagram for a cantilever beam carrying point load at its free end. Consider a cantilever beam of length L subjected to a concentrated load at its free end. Consider a cantilever beam of length L subjected to a point load W at its free end. First, find the support reactions of the beam. Find the support reactions by using static equilibrium equations. The static equilibrium equations are sigma h equal to 0, sigma v equal to 0 and sigma m equal to 0. The sum of all horizontal forces is equal to 0, the sum of all vertical forces equal to 0 and the net moments about any point is equal to 0. Sigma h is 0. Since there is no horizontal force acting on the beam, sigma h is 0. Sigma v equal to 0. Sum of all vertical forces acting on the beam equal to 0. Here in this case, the beam is carrying a point load W at its free end and there induces a reaction at A at fixed end, reaction at fixed end, that is RA in upward direction. Now the beam is carrying two vertical loads. To satisfy the equation sigma v equal to 0, the two forces must be equal. Therefore, equating sum of upward forces to sum of downward forces, that is RA is equal to sum of downward forces W. Therefore, RA is equal to W. Now, let us find the moment about any point on the beam is equal to 0. Let us find moment about A. The applied load W is producing a clockwise moment of intensity W into L. To balance the clockwise moment and to keep the beam equilibrium, to keep the beam under equilibrium, there must be another anti-clockwise moment of same intensity. The sum of moments about A is equal to 0. That means sum of anti-clockwise moments about A is equal to sum of clockwise moments about A. Therefore, MA is equal to W into L. The moment about A, MA is equal to W into L. Now, to find the shear force and bending moment for the cantilever beam, consider a section 1 at a distance of x from free end. Consider a section 1 at a distance of x from free end B. Now, the shear force at the section considered is equal to net force on any one of the side, that is left side, either left side or right side, So, in this case I am considering right side of the section. The shear force at any section is given by the net force on the considered side. The right side of the section we have only one load, that is W. Shear force at the section considered is W. And to give the sign convention for the shear force, I use the acronym RUN. Right side upward negative. Right side upward force negative shear force, and right side downward force positive shear force. So, here the W is acting in the downward direction, therefore, the sign convention for shear force is positive. Right side upward negative, right side downward is positive. So, shear force is plus W, and bending moment at the section considered BMX is equal to W into L, sorry, W into X. The bending moment is W into X. X is the distance of the force from section considered. And now the sign convention for bending moment is either left side or right side. Always the downward force produces negative bending moment and upward force produces positive bending moment. Since W is in the downward direction, bending moment at X, BMX is minus WX. Now, to find the shear force at any section between B to A, we will use the shear force equation, and to find the bending moment at any section between B to A, that is free end to fixed end, we will use the bending moment equation. And these two equations are very much valid between B to A, because if you consider section anywhere between B to A and consider the right hand side, we have only one force W. Therefore, these two equations are applicable between free end to fixed end. That means, to find the shear force at any section, substitute the corresponding X value, the distance from free end. Now, let us find the shear force at B. At B, X equal to 0. That means, to find the shear force and bending moment at B, substitute X equal to 0 in shear force and bending moment equations. Shear force at B is given by plus W, because the shear force is not depending upon the distance. So, its value is constant W, and bending moment at X, bending moment at B is equal to minus W into 0, that is 0. So, shear force at B is plus W and bending moment at B is 0. Now, plot these two values on the shear force and bending moment diagrams. To draw that, take two reference lines, one for shear force and another for bending moment. This is the reference line for shear force, that is 0 line for shear force, and this is reference line for bending moment. If the shear force value is positive, we will plot above the reference line, and negative values will plot below the reference line. Similarly, for bending moment values. Now, shear force at B is positive W. So, draw a line vertically below B, and then bending moment at B is equal to 0. Put a point on the reference line below B. Now, let us find the shear force and bending moment at fixed end, that is A. At A, X is equal to L. To find the shear force and bending moment at fixed end, substitute its corresponding X value. X is the distance of the section considered from free end. Now, I am considering a section at fixed end. So, the X value becomes L. X is equal to L. Now, substitute shear force equation. Substitute X value in shear force equation. Shear force at A is equal to plus W. because if you take section anywhere between B to A, shear force is not changing because right side we have only one point load W. Therefore, it is constant throughout till A. Its value is W. And at A, we have reaction RA, which is equal to W, which is not considered in the shear force equation. Now, at A, considering the reaction also, the net force is equal to 0. Then join this to 0 considering RA. Let us find the bending moment at A. To find the bending moment at A, simply substitute x equal to L in bending equation. Bending moment at A is given by minus WL. Minus WL. So, plot the value. And the bending moment is changing linearly from 0 to minus WL, because the equation for bending moment is BMX is equal to minus WX, which is in the form of y equal to mx, a straight line equation. Therefore, the bending moment is varying linearly from 0 to WL. If we consider the reactive moment at A, which is equal to WL, therefore, the net moment at A becomes 0. So, join the line from WL to 0. The shear force diagram for cantilever beam carrying point load at free end is a rectangle. The bending moment diagram shape is a triangle. This is positive and bending moment is negative. Now, let us have a look on shear force and bending moment diagrams for a cantilever beam carrying uniformly distributed load. Consider a cantilever beam whose length is L and carrying a uniformly distributed load W, say Newton per meter, for example, unit Newton per meter. Find the support reactions first. To find the support reactions, I will take the help of equilibrium equations. Sigma h equal 0, the condition is satisfied as there is no horizontal force is acting on the beam. Sigma v is also equal to 0, but we have two vertical loads acting on the beam. One is UDL acting in the downward direction along with the reaction at the support RA. Therefore, to satisfy the condition sum of all vertical forces equal to 0, the sum of all upward forces must be equal to sum of all downward forces. The intensity of total downward force is W into L. Therefore, RA is equal to W into L. Now, let us find the reactive moment. Sigma m equal to 0. Sum of moments about any arbitrary point in the plane is equal to 0. Now, I will consider the moment about A. MA is equal to WL is the total load which is supposed to act at the center of UDL. The total load of the UDL is W into L, which is supposed to act at the center of UDL, that is L by 2 from fixed end. The total moment is WL square by 2. The moment is WL square by 2. Right. Now, let us find the shear force and bending moment diagrams for the cantilever beam carrying uniformly distributed load over entire length. Consider a section 1 1 at a distance of x from free end B. The shear force at the section considered is the net force on the left side or right side. For this case, I will consider the right side of the section. On the right side, I have UDL over a length of x. The total load acting on the right side or the net load acting on the right side is Wx. Now, the sign convention for shear force is, I will take the help of acronym RUN, RUN, right side upward negative, right side downward positive. Here the UDL is acting in the downward direction, therefore its sign convention is positive. Right side upward forces negative shear force, right side downward forces positive shear force. So here it is plus. And bending moment. Bending moment at the section considered is equal to Wx is the total load, total intensity of UDL, and the total intensity is supposed to act at the center of UDL. So the distance of the center of UDL from the section considered is x by 2. Therefore, the moment is Wx square by 2, and the sign convention for bending moment is either left side or right side. Downward force always produces negative bending moment, upward force always produces positive bending moment. Here in this case, the UDL is downward, therefore its sign convention is negative. Bending moment equation at the section considered is minus Wx square by 2. Now let us find the values of shear force and bending moment at fixed end and free end. To find the shear force and bending moment at free end, that is at B, substitute x equal to 0 in the shear force and bending moment equations. Shear force at B is equal to 0, bending moment at B is equal to 0. Now let us plot these two values on the diagram. Take two reference lines, 0 lines, one for shear force. The shear force is positive, then we will plot the values above the reference line. If the shear force values are negative, then we will plot below the reference line. Similarly, take another reference line for bending moment. Above the reference line, all the values are positive, and below the reference line, all the values are negative. Here the shear force at B is 0. So, put a point on the reference line below B. Similarly, put another point on the bending moment reference line below B. Now, let us find the shear force and bending moment at another end, fixed end. At fixed end, that means at A, x equal to L. X is the distance of the section considered from free end. Now, I am considering the section at fixed end. So, at A, x is equal to L, the distance from free end to fixed end. Substitute x equal to L in shear force and bending moment equations. The shear force at A is equal to plus WL, and bending moment at A is equal to minus WL square by 2. Here in this case, the shear force is 0 at free end and it is changing to a value WL positive. How it is varying? Check the equation. SFX is equal to plus WX. It is in the form of y equal to mx, a straight line equation. So, it is changing linearly from 0 to WL. And at A, reaction RA is also there, which is not considered in the shear force equation. If we consider RA, then net force acting at A is equal to 0. Therefore, join from WL to 0. This is shear force diagram for a cantilever beam carrying uniformly distributed load over entire length. Now, bending moment diagram, its value is WL square by 2, and the bending moment is varying from 0 to WL square by 2 parabolically. If you check the equation, bending moment equation, BMX is equal to minus WX square by 2. So, the curve is parabolic. So, draw a parabolic curve 0 to WL square by 2 on the negative side. At A, we have the reactive moment which is equal to WL square by 2 and not considered in the derivation of shear force and bending moment. Now, with considering bending moment at A, the net bending moment at A is equal to 0. So, join the line from WL square by 2 to 0. Let us summarize the learnings of today's class. The shear force and bending moment diagrams for a cantilever beam carrying point load at the free end and for a cantilever beam carrying UDL over entire length are derived and drawn. The shape of the shear force diagram for a cantilever beam carrying point load at free end is rectangle, and the bending moment diagram for a cantilever beam carrying point load at its free end is a triangle, and the shear force value is constant throughout as it is carrying only one point load, and the bending moment is varying linearly from 0 to WL. Coming to the cantilever beam carrying uniformly distributed load, the shear force varies linearly from 0 to WL positive side, and bending moment varies parabolically from 0 to WL square by 2 on the negative side. With this, we will stop for today and we will meet again with another topic. Thank you.